All right, to summarize the unit so far, we spent a couple of days revisiting, in a lot of ways, equations of lines, and that's from grade 9, and then to some extent grade 10. And we extended it by all the new notation, and that's a big deal. This wasn't review of grade 9, that's for sure. But the properties of lines, what makes them important, is out of grade 9. And but then we introduced that new notation. We spent a couple of days talking about that. Then we spent 3 days introducing this new idea, which is a pretty big deal. In fact, let me go back. We did equations of lines, and then over the last couple of days, we've done intersections, intersection of lines, and that's from grade 10 and to some extent grade 9 even, where in grade 9 we didn't solve systems, but we did talk about two lines and where they cross. But if you don't remember that, that's okay. But you do. But in grade 10, it's a big part of the course where you talk about systems of linear equations and how to solve and find the solution to a system of linear equations. And that's where the two lines cross. We talked about this is again still back in grade 10, talked about the three different possibilities. This is in two space because obviously we didn't introduce three space back then. And we talked about the different possibilities. They might be parallel and distinct, they might be parallel and coincident, or they might just cross at a point, right? And then you do problem solving applications, word problems with them, and you don't get the other two situations. You just get a place where they cross, right? So you do a lot more of just where do they cross. But anyway, we do talk about those. But that's all in two space, and that's all in one notation. So in this course so far, in this unit so far, we've extended the notation. We've introduced lots of new notations. Those notations scale up nicely to three space. That was the big part of it. Remember, there's no scalar equation of a line in three space, so we can't use that. Like, we just can't use that notation when we're talking about three space. Whereas vector notation and parametric notation scales up nicely. In fact, even though we can't visualize what four space would be, the notation would lend itself to that. You could continue on with as many dimensions as you want with parametric notation, right? So anyway, so we introduced those new notations, but a lot of that to me is still connected to ideas that we're familiar with, right? We're still revisiting stuff we've seen before. We're still talking about we're still really just building on things we've done a lot with. Visualization, we've already done a lot of in our past, and tying back to ideas that we've done since grade 9. But we did them in the middle of that sort of talking about lines. We did planes, and to me, that's a bigger extension because that's something brand new. We've never talked about that. Everything you do in grade 9, 10, 11 is in two dimensions. It's on what we call the Cartesian plane, right? X and Y. So the whole plane, the whole graph is just a single flat piece of paper, a single plane. But then when we extend it to three space, we get this big new idea where, hey, we can actually have in three space equations of different planes that aren't just the XY plane, but that are tilted and rotated and all kinds of things. And they have equations and they have properties, and we can do all kinds of work with those. We spent 3 days doing that. So that was a big deal because, again, there's a new notation that's required and all the different stuff that you have to do just generally if you were solving problems in them, like what angle are they at? Is the point in the plane? Find a point on the plane. What are the intercepts? All of that stuff is all brand new. So that was, at least to me, the biggest thing we've done so far that's been new is extending sort of what we've been doing to planes, equations of planes and properties of planes. We did 3 days on that. It's a pretty big deal. Otherwise, we've talked a lot about lines. And as I said, in a lot of ways, that's an extension of what we have already kind of done a lot of in grade 9 and 10. Now, maybe I should have opened with this. I'm going to stop for a second. I'm going to say there is an activity involved with this lesson. So if you are in a position where you haven't done the activity yet, but you are going to, then you should stop now and not watch the rest of this video, because the activity I think is going to be really good. And not only is it a great activity for what we're doing today, but it's a great activity for what we're doing moving forward. And it's just a worthwhile use of your time. And if you're going to be doing it in class and that just hasn't happened yet, then don't watch the rest of this video. Do the activity. Really, 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 the thinking that you're going to do on your own is worthwhile to do without having sort of let the cat out of the bag, which is what we're about to do in this video. And, you know, some people think it might be fun to have advanced knowledge of what's happening, and that might be funny for you, but really it's going to make the experience worse for you, and it's going to make your learning worse. So stop now, don't watch anymore, wait to do the activity. If you're not doing the activity in class, but you are going to be able to some other way attend the activity virtually or something like that, then again, don't continue watching. Stop now and figure that out and see if that's going to happen. Okay. That being said, if that's not going to happen, keep watching, and we're going to summarize the activity, and we're going to, but I'm going to kind of like blow it in a second here. But you know, it's not going to be the end of the world. And for what we're doing today, the maybe danger is it's going to seem really easy in a way. What we're going to actually end up doing is algebraically not going to seem that hard. But to me, there is thinking that's more important than anything, that the activity is going to allow you to have the time to do that. All right, so that's all I'm going to say. Last chance to pause before I spoil it. If you're going to have any opportunity to do the activity, you want to stop now. Otherwise, here we go. So we're talking about intersection of lines and planes. And like I was saying, to me, this is a bigger extension than what we've done so far, because lines and lines, even though we're doing in three space, and there is the fourth possibility in three space of lines intersecting lines, and you know, dealing with direction vectors and parametric equations as we've done, that is all very different and very new and really cool, absolutely. But it's still, I feel like still within the realm of stuff we have experiences with. Now we're talking about intersection of lines and planes. And what we're going to do next is going to be even bigger, but we're not doing that today. So I'm not going to talk too much about that. But today we're going to talk about lines intersecting planes. And this is, to me, a bigger sort of step into a new world than some of what we've done. So the thing that we hopefully learned from the activity is, and if you did the activity, a big part of that is convincing yourself that there are only three possibilities, that there aren't more. It's great when somebody just tells you and confirms that for you, that it's true that there's three possibilities and no more, but it's better if you can confirm that somehow for yourself and say, like, listen, I can visualize this, I understand there's not going to be another way that they could interact, right? So there are three possibilities. That's one of the big takeaways from the activity. If you didn't get to do the activity, don't lose any sleep over it. It's not the end of the world. It's too bad, but that happens. But it is a good activity. It's great. And it just allows you to think through this stuff on your own. And if you can kind of develop these thoughts and make the connections yourself, you're going to remember them longer. You're going to remember them better, more quickly, be able to make better connections with them, with other material, that kind of thing, right? That's why it's good for you to come up with it yourself instead of just memorizing what somebody else has told you. Okay, so, but what we are talking about today is intersection of a line and a plane in three space. One line and one plane in three space, obviously, otherwise in two space that wouldn't be all that interesting. And there are three possibilities. That's one of the big takeaways. And in all situations, you know, two lines intersecting in two space, or two lines intersecting in three space, or not intersecting, as maybe the case is, there are different numbers of possibilities. So knowing how many possible outcomes there are is a big part of it, as we've talked about. And then the next step is algebraically, what does that look like? How do I interpret the algebra to determine which of the possibilities I'm in? And then have I shown enough work to make my final conclusion? Or do I have to do some more work and actually find the solution and then state the solution? Like, those are all the things that are going through your mind, right? And as we've said, we're doing a whole bunch of different ones of these, and they start to mix up with each other. So keep all of that in mind. But when considering the intersection of a line and a plane in three space, there are three possibilities. And this is where, in a room full of students, I would say, from the activity, what are they? what are the three possibilities? And I don't know necessarily what they would come up with as the first one, but let's say I don't know if it's the main one, but it's maybe the most interesting one is where there is one solution, and that is where the line passes through the plane. Okay, so I'm going to try to draw the plane like this, where I can go like this. Let's see how that does. Nice. Okay, so I've got my plane, and in fact, I'm going to use my ruler to really make this look nice. And so my line is coming through. Oops. Okay, so I have my plane, which I'm going to call pi. I have my line, which I'm going to call L. And this has one solution. And the line and plane, whoops, um, hopefully we've already noticed by now, just from the 2 days of talking about lines, that the geometric interpretation is a big part. How we describe it, the words that we choose, that we use, which I'm going to tell you what to say, and you should just do what I tell you. But it is important. We're not in any way just flippant about how we describe these things. Okay, so the line and plane cross at a point, which means there's one solution. But another way that we think about this is that the line passes through the plane. Could we have thought of, sorry, let me get this down, passes through the plane. Could we have thought of one line passing through another line in 2 space or 3 space? Sure, we could have done that. So when we were talking about intersection of lines, we could have talked about it that way, but it would seem strange. The fact that the plane has more dimensions than the line to us makes it feel like it takes up more space, which is a strange thing to think about comparing length and area. But anyway, I'm not going to get into that conversation right now. But it sort of seems natural to think of a plane as existing and the line just passing through it, right? If I have a target for a bow and arrow and I shoot an arrow at it, I would think of the arrow going through the target, not them intersecting or with each other, right? Now that's because the arrow is moving, but anyway, again, I'm not going to get into that. So it's reasonable to think of this as the line passes through the plane, but really the best way I think that we want to think about this is the line and plane cross at a point, because that's how it has. We've talked about that in the past, where two lines cross or meet at a point, intersect at a point, right? And that has one solution. And the solution is thus. That's going to be the next part, obviously, figuring out what that means. The next one, okay, will be, here's my plane. And how about this? The line, and I think it would kind of look like this. Here's my line L, here's my plane pi. The line is in the plane, okay? Or we have another way of saying that, I'll get to that. And this is infinite solutions. It's very common for us to think about the geometric interpretation, but also to differentiate these separate possibilities as the number of solutions. So there's the one that has one solution, there's the one that has infinite solutions, and then there'll be the third one. Okay, and this one has infinite solutions. Now this is different because these are not coincident. In fact, this is awkward for students the first time thinking about this because they say, oh, they're coincident. Not really. Coincident means they both take up the same space. And that's not true because the plane takes up more space than the line does. So it's more like the plane contains the line or the line is in the plane. That's what we would say, one of those two things. So, but there are still infinite solutions, but the solutions aren't everywhere. The solutions are just where the line is. The plane exists in places where the line doesn't. So this is an infinite solutions that's a bit different from what we've seen in the past, okay? So let me do the two descriptions. The line is in the plane, Or we might say the plane contains the line. And these are both different ways of saying the same thing. Okay. And notice that if you're doing this for your note and you're writing it on your own page, there's a little bit of extra space here at the bottom, and that's on purpose. So I've got these boxes and I'm leaving some space because I'm going to come back and add something in there after when we talk about how we actually solve these. And the third possibility is the one where there is no solution. And that is where I have my plane like this, let's say, and I'll do my line like this. Okay, so they're just separate, but very specifically, there's a time when this is going to occur, and that is where the line and plane are parallel and distinct. Okay, so this is important that although it kind of actually looks like they're not parallel, maybe because of how I chose to draw the line, but we would say that they are. And because if they weren't at all parallel, then the line would pass through the plane eventually. And this is something that, back in grade 9 or grade 10, is a new idea that, okay, they don't cross yet on the graph, but if they're not parallel, they'll cross eventually, right? So same thing with a line and a plane. That's something we have to think about, come to terms with, that just because they haven't crossed yet, if they are at an angle to each other, they will cross eventually. The line will eventually pass through the plane. Hey, I think that's something that you can understand. Now, the next part of the activity. So if you haven't got there yet, you may have got there, but if you haven't got there yet, then the next part is to determine how we actually find the solution to one of these. And so I'm going to try to give you a chance to think about this for yourself, because again, if you can make the connection for yourself, you'll remember it longer, maybe forever. But maybe you already have during the activity, although this is a bit of a harder leap. So if you didn't get there, if you did the activity and didn't get there, that's very much okay, very reasonable. This is a bit of a stretch, although when you see it, you might kick yourself and say, oh geez, I wish I had noticed that. Okay, now to make this connection, the easiest way is to look at an example and look at a particular example. Here I have two equations. One is in scalar form. This is three space. We're never going to cross two space and three space. I'm never going to have a line in two space and a plane in three space. That would be weird. Okay, so these are both three space. When we're talking planes, we're always talking three space. Okay, so I've got a scalar equation. Automatically, I know it's a plane because it's scalar, and there is no scalar equation of a line in two space. Plane are often with pi, but again, that's not necessarily a rule. Somebody could try to trick you and call a line pi, right? But I know because it's scalar and it's three space because it's got x, y, and z, that's definitely a plane. And this is a line. Good question. How do I know this is a line? Because you can have parametric equation of a plane in three space. How do I know this is a line, aside from the fact that it's got an L? Can you answer that question? The answer is it's only got one parameter. Equation of a plane in parametric form would have two parameters. It would have SNT or MNT or whatever it is, right? It would require two parameters. Think about vector form. That's something we've seen more. Vector form of the equation of a plane has to have two direction vectors, non-collinear. So you would have two parameters. So I know this is a line because it only has one parameter. I know it's three space because it's got X, Y, Z. Same thing here. So right away, I can identify that this is a line in a plane. And in fact, on the test at the end of the unit, that's something you're going to have to be able to do, because look, for each system, give a geometric interpretation, state the number of solutions solved in the system where possible. So these instructions are these instructions are the same as solving a system of two lines, right? So there's nothing about the question that's going to tell you what you're dealing with. You have to be able to recognize this as a line in a plane. Okay, before we get there, this one happens to be in scalar form and parametric form, but it wouldn't have have to. This one is, but it wouldn't have to. We could do these with given other forms, and I bet we will. But this is the form that I'm going to give you the little hint. It's probably the easiest one to think about how we're going to solve. So I want to give you a second, and you can pause the video. I'm only going to wait about 5 seconds because you can pause. But I'm going to give you, pause if you want and think about this yourself. But what strategy do you think you could use to try to solve this? What might you be able to do? And I would say that in a room of 30 people, usually there's somebody that makes this connection. And here's the next tip. What does it mean when it says x equals? It means x is that. So if x is that, what is this x? I mean, if they are crossing, then it's the same x. That's what it means for two things to cross each other. They're the same x in the same time. So this x has to be this x. So maybe you've thought of it already, and usually what somebody says is, oh my gosh, you don't just take these and put them in here, do you? And oh my gosh, yes, that's exactly what you do. In fact, that's all you do. So even though this is like a big extension to me, where we're really growing our world and we're extending stuff we did way back in grade 9 and 10 to this idea of three space and lines and planes, this idea of planes, this is probably the easiest one, okay? This is, in a lot of ways, this has a very straightforward process of how we solve, and it's easy, the algebra, that kind of thing. And so let's go ahead and try it. We'll see what happens when we do it. But if you were thinking about this, fantastic, good for you. Well, if this is x and this is x, do I just take this and put it in there? Well, oh my gosh, let's give it a try and see what happens. Okay, so I've got 4 times x, where x is 2 plus 7t, minus y, where y is 3 minus 14t, plus 6 times z, where z is 10 minus 7t, 7t, not 70, minus 12 equals 0. All right, so now I'm just going to expand and simplify. I mean, you might say, well, do we do that? And I've kind of already said, yes, that's what we do. But if you were figuring this out on your own, you'd say, well, okay, now what do I do? Well, I've got an equation with one variable. It's just a t. So how about we solve and see what happens? Like, how about we solve for t and see what happens? So I've got 4 times 2, 8 plus 28t minus 3 plus 14t plus 60 minus 42t minus 12 equals 0, or equals 12 if you want to move it over. And this works out to 28 plus 14 minus 42 turns out to be 0. So 0t, and then when I move all the constants to the other side, I'm going to do that in one shot here. But I'm just taking the 8, the negative 3, the 60, and the negative 12 to the other side, and I think it works out to negative 53. So now I have something that I need to interpret. And this is going to be the big part of this, as we've seen in the past, is the interpretation is always a big part of it. How do I interpret it? How do I state my solution? And what do you think the interpretation is? And again, I would encourage you to pause and think about it. But I would also remind you, we've seen this before. And this is something that's never true. So what does that mean? That means that the line and plane in this case are parallel and distinct. Therefore, L and pi are parallel and distinct. And that means there's no solution. And we're done, because we can't find a solution if it doesn't exist. So I hope that makes sense. Let me go back up here because there's something I want to fill in to this handout. We figured this one out. No solution is when 0 t equals k, some constant, because this is never true. So what would happen if I had infinite solutions? Can anybody think of that? Because we've seen this before, and no matter what we have, we're going to get sort of t equals something, right? Like that's what we're solving. We're solving this equation in terms of t. So what would it look like if we had either of the other two, one solution or infinite solutions? Let's do infinite first if we can. We're going to get 0, t equals 0, because this is always true. Okay? And so what would happen if we get one solution? We're going to get t equals k. We're just going to get a value for t. We're just going to get a value for the parameter t, and that parametric value, the value of that parameter, is going to be where the x, y, and z occur, right? Because I could sub that back into parametric form and figure out what the x and the y and the z are. So those are the three possibilities. So what you need to know for this, after all of the activity and all the thinking and all the talking that I've done going on, is you just take the x, y, z, sub it in, and you got to remember those three outcomes and what they mean. And we've already kind of seen what they mean in grade 10. It's very similar. Again, this is a nice extension of stuff we've already seen, we already know. Okay, cool. But that's the last part of this top of the handout, is outlining those three possible equations. And actually, that's not the last part. I'm going to add one more thing here. And how we're going to say how you do it, what the three possibilities are, and sort of what the algebraic outcome is. Okay. So let me add this in. If you didn't leave space here, that's fine. Do it below. But to solve, we simply sub the line in parametric form into the plane in scalar form. And that's it. So this, you can memorize this. Like, this is super straightforward. Now that means if you're given a question where you don't have scalar form, you don't have parametric form, what does that mean? It means you got to go and get those, right? So we've done a lot of work with that. We did days and days of working with converting between forms, and that's what you would have to do 100%. But you've got a goal. You need that, you need the plane in scalar form, you need the line in parametric form. Easiest way, sub and solve, that's it. You need to know how you interpret your outcome, but then you're basically done, right? Could you do it given other forms and without converting? In certain circumstances, absolutely, but it's still going to be way more work. And in some circumstances, probably not easily. So it's just not worth it. Yes, we're going to talk a little bit about this. Yes, there are other things that could happen, but generally speaking, for this one, this is the way we want to go about it. We've got a procedure that's going to work. It's efficient. It works every time. Let's take advantage of that. Okay. I don't know if it's good to talk about this now or talk about this later. I suppose we could just talk about it now. What does it mean that these are parallel and distinct? Like, what does it mean about the properties of each of these? In other words, in systems of lines, we've got tricks where we can narrow down the possibilities, and at least in some cases, with a quick little trick, decide, at least to some extent, what's happening and maybe save ourselves some time. So what would be the case here that would help us with that, that would cause that? How would you be able to tell that a line and a plane are parallel? Well, if a line, here's the thing, planes have multiple direction vectors. So I can't just decide if a direction vector is parallel to a direction vector of a line, right? In fact, let me draw this here. If I have a plane I have direction vectors going all over the place. And if I have a line, it may or may not be parallel to any of those. But what will be true if the line is parallel to the plane, it will be perpendicular to the normal of the plane. So you could find the normal of the plane. And how can you tell if two vectors are perpendicular? You take the dot product and see if they're equal, or equal to zero. See if the dot product is equal to zero. That could tell you if they are parallel or not. But you're going to see, I won't do this for this one, but we'll talk about it for another one, and we'll see that it probably isn't the best use of our time. Okay, but that's something to think about. We'll come back to that. Let's try another one. Okay, so now we're just going to look at different examples and sort of see what their outcomes look like. And obviously, looking at this one, explore what happens when we have them in different notations, that sort of thing, right? But there's no trick. We want parametric form of the line. It's not in parametric form, so I'm going to put it in parametric form. I kind of already started talking about this, I guess. Are there situations where maybe you could narrow down some of your, yeah, maybe, but you know, really, I don't know that you're going to save yourself time. So I'm just going to throw this into parametric form. 5 plus 2t, y equals -5 minus 5t, and z equals 2 plus 3t. So there's my line, and I'm just going to sub them in. I mean, there's not that many, there's not very many times in this course, or even in advanced functions, where there is a process so straightforward and easy that we can just use it every time and it's just going to work, and interpreting is relatively easy. So like, you know, I'll talk about, oh, there's other things we could think about, and probably everybody out there is like, why would I think about stuff when this is so easy for me to just do? Just all I have to do is plug that in. You're telling me that's going to work every time? That's all I have to do? Okay, stop talking. That's what I'm going to do every single time. I get that, and that's fine. That's good. 65t minus 4 minus 6t equals 29. And in this case, we get negative 53. T equals 53. So t is -1. So what does that mean? That means I got a value for t. I can use it to figure out what the point is. And that point is where this line will pass through the plane. They intersect at a point. That's what this means. I want to know that. I need to know that that's what that means. But I'm done. Okay, so that means from the parametric equation up there, okay, from the line, because I don't have the parametric equation of the plane, so I'm using the line. So x is 5 plus 2 times -1, which is 3. Y is -5 minus 5 times -1, which looks like 0. And z is 2 plus 3 times t, which is -1, which works out to -1. And we're done. Therefore, the line and the plane intersect at a point. And that point, the solution, one solution. Ooh, almost missed that. One solution. And that solution is 3, 0, -1. Okay, easy enough. We had to recognize that this is not in the right form, so I had to put it in parametric form. But then all I did was sub in get something and then interpret that something. Okay, let's keep going. Again, I've got scalar form of a plane, vector form of a line. Let's take that line and put it in parametric form. Oops. Let's sub in. Just expand. And this looks like I get 0t. Hopefully I haven't made any little typos, but this one is supposed to work out like 0t equals 0. And again, that is always true. So we have to interpret this as our solution. And it means, therefore, L is in, so lies inside. Okay, we don't say they're coincident. It's a subtle difference, but it's important. L is in pi. The line is in the plane. There are infinitely many solutions. Now, this is something that we take for granted in other situations when we have infinitely many solutions. But in this case, we are actually going to state what the solution is because there's infinitely many solutions, but it's not the entire plane. Okay, so what is it? It's just the line. It's all the points that are on the line. So the solution is the line. L, in this case, has a name, so I just call it L because it's the line. Okay, the solution is the line. So the solution, or I could even better, I could say the solution is the line x, y, z, but it has a name, so I can just use the name. But this is how I can identify a pattern of an infinite number of points, right? And all the points on that line are also in the plane. And so that line, that equation, is the summary of all of the infinite solutions to this system. Okay, so you can just say is L, or you can say is the equation of the line. And the equation of a line being a solution is something that we will see again. So that's important to think about. Okay, but you don't have to say the equation in this case. You can just say L because it has because it has a name. Okay, but it is the line is in the plane. That means the solution is the line, all the points on the line, which is what a line is. Okay, so that's each of the three, I believe. We saw parallel and distinct, no solution. We saw line in the plane, infinitely many solutions, and we saw intersecting at a single point. Now we're going to do one more to talk about something, but this is not a different situation because we have um, seen all three, and there's only three. Okay, but what if we wanted to do this? This is what I talked about before. What if we wanted to do this? So what if I just looked at the direction vector of this line, which looks like -3, -7, 0. And I looked at the normal of the plane, 7, -3, 5. And I did n dot d. And what is it? Well, 7 times -3 plus -3 times -7. So that's -21 plus 21 plus 5 times 0. So plus 0. So that's 0. So what does that mean? That means direction vector of the line perpendicular to the normal of the plane means they are parallel, right? Therefore, line is parallel to the plane. So what could we do? Check. If the point, any point on the line is in the plane, check that. And that will tell us if the whole line is in the plane. So what's a good point? How about the point of the position, the given position vector? So when I check this, how do we check if a point is in a plane? With scalar, which we're given, which we have. So 7 times x minus 3 times y plus 5 times z minus 12. 28 minus 12 plus 5 minus 12 is 9. Right side is 0, not equal right side. Therefore, The line and plane are parallel and distinct. And so there's 0 solutions, no solution. Whoa, that's weird. No solution. Now I'm just going to go back and explain what happened here. This is an alternate way of approaching this, I suppose, that matches what we talked about with lines and will match to some extent what we're going to do moving forward. So it's useful to think about this because I think there'll be questions about, oh, wait a minute, why didn't we talk about that? So we are talking about this. But planes and direction vectors don't necessarily play that nicely together. Direction vectors don't tell us everything we want to know about a plane. So a direction vector for a plane is not going to help the way it did for lines. But a direction vector of a line does help. So what we did was we looked at the direction vector of the line, compared it to the normal of the plane, and this goes back to properties of planes, and if their dot product is 0, if they are perpendicular, that means the line in the direction vector is parallel to the plane. Okay, so you got to get that. That's something you got to get anyway. So hopefully you understand that. If you don't understand that, you got to go back to those days of planes and vectors and think about that, okay? Because that is something, even though we don't need it to solve this, we do need to understand that. Now, in this case, we determined that they are parallel. So we decided to check a point, and if they're parallel and a single point on the line is in the plane, then every point on the line will be in the plane. That's what parallel means. Can I check a point? Can I check some other point in the plane and see if it's on the line? No, because there's going to be lots, infinite points in the plane that are not on the line. Go back and look at the visual representation that we drew up at the top, and that'll be pretty obvious. But every point on the line will be in the plane. Okay, I hope that's good. I'm going to stop there for a second. I hope that makes sense. So this is a perfectly viable solution. This worked. Let's quickly compare that to what if I had done this? What if I had taken the equation of the line, hold on, or I took the equation of the line and I put it in parametric form. Y is 4 minus 7t, and z is 1. Is that right? Yeah, because we had a 0 in the direction vector. Nice. Okay, so z is 1. That's easy. And I sub that into the equation of the plane. 7 times x minus 3 times y plus 5 times z. Z is just 1 minus 12 equals 0. That was just a scalar equation of the line that we were given. 7x minus 3y plus 5z minus 12 equals 0. So this works out to 28 minus 21t minus 12 plus 21t plus 5 minus 12 equals 0. Take a look at how subbing the point in was basically that, and doing the dot product was, and expanding the other part, sorry, of the brackets down there was basically doing the dot product. Like basically, when I did this, I was just doing each step of this process, and I just did it separately because this works out to 0t equals -9. And so we would say, therefore, because we got this, and that's one of our 3 outcomes, the line and plane are parallel and distinct. And there's no solution. Okay, so in this case, this worked. I'm not going to say it was more work. I'm thinking it's about the same amount of work. But what I am going to say is that if I didn't get them to be parallel, then this would be more work. Like there are instances where I think comparing the normal and the direction vector, and this is the only time I'm going to say this, because in other cases I'm going to say it's worthwhile, because you can usually do it quickly, and it's just a good thing to think about, because it's also just good to think about those as being important properties. But in this one case, I'm going to say maybe this isn't worth it. Maybe you just skip this part and you jump straight to this because this is always going to work and there's only 3 cases anyway. And even in the case where this system works, it's not really less work. Like this got us the answer. It's not more work, but it's not really less work. So, and there are cases maybe where this is less work. Because if I get to the dot product not being 0, I know what I'm looking at. I know I'm looking at a place where there's one solution. But then I just have to go and do this anyway. So maybe I might as well have just done that in the first place and save myself some trouble. Okay, but it is up to you. You can do one or the other. The one thing I will say is, what if you have a question where it says, determine the number of solutions without solving? Aha, then you wouldn't be able to just sub in and solve necessarily, right? So there are still certainly situations that we can fabricate, or just generally speaking, where we want to know how to compare a plane and a line and understand that it's the direction vector of the line and the normal of the plane that is going to be important, right? So that is definitely true. But if all we're doing is solving the system, then I would say that probably the most efficient way of doing it is just doing it the same way every time, like we did here. Okay. All right. Good luck. This is the one we're only doing 1 day on. We did 2 days on intersection of lines, only 1 day of lines and planes because it is so straightforward. Hopefully we wrap that up nicely. And you're still visualizing whether or not you got to do the activity. It's still great to visualize this stuff because it is going to be so important for everything that you have to do on quizzes and tests, but also for what is coming next, which will involve another activity. So there's lots going on. Okay, so keep all that in mind. But this is the easy one. Hopefully, bit of a break today. But keeping it in the bigger picture of all the other systems that we're going to be looking at and that sort of thing, and generally just looking at properties of these things, right? It's neat to think about and look at all of this stuff. But that is intersection of planes and lines.